Uh, Good morning, everybody. Our first research talk today is by Professor Lalitha Vadlamani, and our session chair is Professor Vinod Prabhakaran. Professor Vinod Prabhakaran is a faculty member at TIFR Mumbai. He received the PhD degree from the UC Berkeley, and he was a postdoc at UIUC and EPFL. His research interests include information theory, communications, cryptography, signal processing, and he has been an associate editor for transactions on information theory for past several years. Also, Vinod is also on the advisory committee for this summer school, and I thank him for all the suggestions and supports through last 2 years. Uh, yes, Vinod. Thanks.
Thank you, Satyajit, and thanks a lot for organizing this wonderful event, which I'm sure the students have been benefiting a lot from. So without taking up too much time, let me introduce our speaker today. It gives me great pleasure to introduce Professor Lalitha Vadlamani from IIIT Hyderabad. So she received her bachelor's degree in electronics and communication engineering from Osmania University, Hyderabad, and ME and PhD degrees from Indian Institute of Science, Bangalore. And from 2015, she has been a member of the faculty at IIIT Hyderabad, where she's affiliated with the Signal Processing and Communications Research Center. And between her master's and PhD degrees, Lalitha worked in the industry at Qualcomm and Connection Systems. She has also interned at Microsoft Research in Bangalore. Her research interests include coding for distributed storage and computing, index coding, polar codes, learning-based codes, and coded blockchains. She has received awards, the Professor ISN Murthy Medal from IISc in 2005, and the TCS Research Scholarship. Let's welcome Lalitha to deliver a lecture on codes for distributed gradient descent. So just a quick announcement that please, Lalitha has indicated that she welcomes questions. So please put your questions in the, raise your hand. You probably already know the drill, but please do ask questions if you have any. Lalitha.
Thank you, Vinod, for the introduction, and thank you, Satyajit, for inviting me to give this talk. I mean, I really look forward to go to IIT Mandi sometime. Maybe not, not this year, but yeah, whenever it
Most
works.
welcome. Yeah.
Yes.
All of you.
Yeah, thanks for the wonderful organization. So today I'm going to talk about codes for distributed gradient descent. So this is joint work with Sahasrajit and Nikhil. Sahasrajit, when he was doing masters, I think dual degree from IIT Bombay. Now he is in Stanford. And so one part of the work is joint work with them. And the second part of the work is joint work with Chanuja, Vaneet, and Professor Sundarajan. So this is just a quick outline of the talk. I'll give a motivation of distributed computing and why coding has some role to play in the problems of distributed computing. And I'll introduce a gradient coding framework. This is background. And there are two variants of gradient coding which we will consider as part of this talk. One is approximate gradient coding and the other is tired gradient coding. And so distributed computing setting. So just a very quick motivation. I think this field doesn't require that much motivation now, at least I think. There are machine learning applications everywhere, and there are huge clusters which are performing distributed computing tasks all the time, like Apache Spark, Hadoop, MapReduce, etc. And these applications run on thousands of nodes. So just to formalize the setting a little bit. So the framework is as follows. So there's a master, and there are some worker nodes, and the worker nodes are not communicating among themselves. It's only the master who keeps a track of the overall picture. It's like the workers are like just doing the task which is given to them. So that's all that they do. So the master takes the responsibility of splitting a job into multiple tasks and exploiting the parallelism of the compute resources which are available from the workers. So a job is split into multiple tasks, and the master assigns some tasks to all the workers which are given to it, and the workers themselves return some functions of I mean, here you can think of as if x1 tilde up to xn tilde as some data which was sent to the worker nodes, and the workers themselves are computing some function of the data which was assigned to them, and it is returning. The master kind of accumulates or aggregates all the function values, and the computes the aggregate job output, whatever it is. So this is slightly, I mean, I am telling from an abstract point of view, and I'll give the gradient computation is one such example. Okay? There are others also which can be done in this way. So what is the problem of stragglers? The problem of stragglers is that among the worker nodes, there might be a subset of the worker nodes who are taking, somewhat actually arbitrarily long time to finish the task which is given to them, right? And so that kind of kills the parallelism somewhat, because master requires the outputs from all the end nodes to be able to compute the job output itself, right? And these stragglers are the workers which take much longer than, let's say, the average, are the ones who are the bottleneck to the job completion time. So this is a figure taken from a reference, the first paper of gradient coding, where they motivate that the straggler problem is something important to look at. So here is a figure which shows some statistics as to as a function of the workers, what is the average time that the workers are taking. So this is a set of 50 workers, and as you can see, there are a bunch of 8 to 9 workers who are taking considerably more time than the rest of them, and these 8 to 9 workers, they form the bottleneck in the job completion time. So the problem is important. I mean, it is seen in practice. So how to kind of mitigate the effect of stragglers is to somehow introduce redundancy in the computation itself. That is by saying that I'm not going to send disjoint pieces of data to all the workers, in which case every computation that they are doing is unique, and that kind of adds value to the master. So but if that is the case, there's no redundancy. But we can introduce redundancy by, let's say, things like even simple replication. Like the same task is, let's say, being performed on 2 different nodes, then I need not have to wait for the straggler to be able to return. Maybe some other node is sending me the output, right? So that is a quick idea of what is meant by introducing redundancy among computations. And we'll see more ways of introducing redundancy in the computations. And as I said till now, the distributed computing framework that we are looking at is general enough, and there are at least 3 problems of interest which are studied in the information theory community, studied very widely in the information theory community. And the 3 problems, each of them have different solutions, and that is the reason they're somewhat the actual solution that you use for each of these problems is different, and we are going to look at one of it. The first problem is matrix multiplication, and this is something which again regularly happens, and it requires distributed computing. The gradient descent, and the third one is polynomial evaluation, and we are going to look at gradient descent application today. Okay. So distributed gradient descent. So I'm just going to talk about the gradient descent problem itself, and then distributed is kind of I'll tell you what it is. So if you have a data set with a small d, capital D with small d examples, which is, the kind of the data set that we have is input output kind of data set, xi's and yi's, and maybe we are trying to fit a function to that. And as part of your neural network learning this function, so there is a certain loss function which you try to minimize, and this loss function is itself parameterized by a parameter called beta, right? So the beta is part of the, let's say, function that you are learning, right? The loss function, we are looking at specific loss functions which are like decomposable in some way, right? So the loss function itself can be expressed as sum of loss functions of at individual examples, and there are d of them. And I mean, it's very well known that gradient descent is used for learning this parameter, and the gradient itself is again a, I would say, yeah, here in this case a linear operation, right? At least with respect to the sum, right? So this can be parallelized because as you can see, it is decomposable. And the way the parallelization itself is done is that the data set is split into some number of partitions, okay, d1 to dk, right? This can be thought of as, if you want, disjoint partitions of the actual data set. And the gradient which is computed on one partition of the data set will be termed as the partial gradient. So this gt, gj of t is the gradient which is computed over the partition dj, right? And it's the sum of these gj's which gives the actual gradient that we want for updating the parameter beta itself at iteration t. So this is what partial gradients are. And so what the master actually does is sends these data sets to the workers. They compute the partial gradients and send them back to the master, and the master computes the sum. So as you can see, at the master, it's like very compute light task that way. Okay, the actual heavy computation is only happening at the workers. And that is one important aspect of distributed computing. I mean, the master itself doesn't do any heavy computation. Okay. So these are the partial gradients. And again, if there are no stragglers, this particular thing is absolutely fine. It works fine, and you just accumulate all the GJs and get the GT, right? But if there are stragglers, so I'm directly going to only the gradient coding solution. Maybe you could think of some form of repetition, but actually even as part of gradient coding, we can see that. So I'll come to some repetition codes also in subsequent slides. So in gradient coding, what happens is, so suppose this is a setting in which there are 4 worker nodes, and so the number of partitions that we make the data into is somewhat in our control. I mean, it's like in this case, we choose to do 4 data partitions. And what it means is that one thing I would like you to remember is that this D1 to D4, right? The size of this is going to be 1/4 of the original data set. Okay, so that fraction is something which I want you to keep in mind. And it always depends on the number of data partitions that you're doing. Okay, so in this case, we choose to do 4 partitions, okay, D1 to D4, and the master sends, let's say, D1, D2, D3 to W1, D2, D3, D4 to W2, and so on. The workers compute the individual partial gradients, which means they compute G1, G2, G3. Okay? So they are doing computation on all 3 separately. But what they are doing is, in terms of communicating to the master, they are sending only the some linear combination of these 3 gradients. Okay? And each one of the workers are going to do the same. Right? So what is the computation load per server in this case is actually 3/4. Okay, it's, I mean, and the number of stragglers that you can tolerate. So if you were just assigning one of the partitions to each of the nodes, right? So the number of stragglers that you tolerate is 0. Even if one of the worker nodes straggle, then we'll not get the gradient for that part of the computation. right? I mean, that partial gradient is missing. So now in this case, I mean, we can show that there are two stragglers which can be tolerated, okay? And which means that even if, two worker nodes do not send their linear combinations, from the other two worker nodes, we can compute the linear combination that we want. But what is the linear combination that we want is G1 plus G2 plus G3 plus G4. So this is what we want, right? And as you can see, you cannot compute it whatsoever just from one worker node, because one worker node has definitely one data point less, right? So that way it can never send the sum of all the four gradients. So that is not possible. 2 is the minimum that you have to contact, and in this case 2 is sufficient as well. Okay. So there is a lower bound on the computation load, given all the parameters that we have discussed till now. One is K is the number of data partitions, N is the number of worker nodes, and S is the number of stragglers. Okay. So D, I would call it is the number of data partitions assigned to each worker. And in that sense, D by K is the computation load, because as I said, when you're doing K data partitions, one data partition is of size 1 over K, right? So the total number of, the computation load of a particular worker is D over K, and that is lower bounded by S plus 1 by N. And in the previous example, if you just plug in these parameters, the computation load is such that we can actually tolerate two stragglers. Okay, it is S plus 1, which is 3 by 4. Okay. And this lower bound is pretty easy to derive. The reason is that each data partition whatsoever has to be placed at least in S plus 1 workers, because suppose if a data partition is placed only in S workers, and if those struggle, then the gradient for that data partition, there's no way we can recover, right? So, and this actually comes from a simple counting that way. So the way to do it is, your D, which is the computation per worker, into N, which is the total computation, if you want to call it, right? It has to be at least K times S plus 1. So it is, two ways of counting the same thing, and D times N is a lower bound on K times S plus 1. And that's as simple as it can get. Okay. So now, so the gradient coding itself, whatever we have seen here, right? The linear combinations here can be represented using an encoding matrix. Okay? And the encoding matrix, I will call it A. Yeah, I think maybe I would have, I'm not sure if I've given the dimensions here or the size here, right? But all the linear combinations that each one of these nodes is sending, you can represent using a matrix. That's all that I'm looking at, and I think it's an N by K matrix, yes. So what is the requirement of this matrix, given that you have to be able to tolerate any S stragglers? So there's a simple requirement, is that for any subset I of N, which is of size N minus S, so this I represents the set of non-straggling nodes. Okay, and this could be arbitrary. We require that the all ones vector be in the span of the encoding matrix. Okay, so this condition, whatever I'm calling it as a span condition, kind of gives you the requirement on the coefficients which the worker nodes have to pick in order to send their linear combination. So because as we have seen here, right? So all these AI prime, A1 prime, B1 prime, C1 prime, etc., they cannot be picked arbitrarily. There is a condition that the coefficients have to satisfy, right, to be able to tolerate, here in this case, any two stragglers. And the condition that they have to satisfy is known as a span condition. And the span condition is just thus, that for any subset of N, 1 to N, such that, of size N minus S, the all ones vector should be in the span of that. Okay, and once we do that, why is this condition necessary and sufficient kind of for the master to be able to recover the sum of the gradients, is because you can take the linear combination, you can take another linear combination of all the linear combinations which the worker nodes are sending to be able to recover this all one, and all 1 multiplied by G1 to Gk is actually the sum of the gradients that we want, right? So this is the equivalent condition for that. So I'll describe 2 sets of codes, both are quite simple, which kind of achieve the lower bound that we have seen in the previous case. So this is the lower bound that we have seen, d over k is greater than or equal to s plus 1 over n, right? And I'm going to describe 2 sets of codes which achieve that with equality. One is fractional repetition. The idea is very simple, and for this code construction, all that we require is that s plus 1 has to divide n. Okay, and if that is the case, I think this is the simplest code that we can think of. Okay. So all the d1 to dk. So in this case, actually, if you see, it is d1 to d6. Okay. They are grouped, or actually they are partitioned into s plus 1. So each worker has to be assigned s plus 1, right? So the way it is done is that it is just, I kind of go from worker 1, I'll assign the first 3, I'll go to worker 2, assign the next 3, I'm done with the data set. Repeat that for the next set of workers, how many ever they are. So as you can see, there is a repetition of the exact pattern which is assigned to, let's say, w1, w3 and w5, and the other group which has this is the w2, 4 and 6, right? And that's why it's called fractional repetition. The scheme is very simple, and the general scheme is just as simple as this example, let's say, right? And each worker node is sending the simple linear combination of these, right? And how do we know this scheme actually tolerates stragglers? It is because, if you see the number of nodes in which any partial, one particular group is present, which is this d1, d2, d3, is s plus 1. And even if there are stragglers, at least there is one copy of that which is present, and that's why you can recover the gradient, right? So the fractional repetition is very easy, and it works for whenever s plus 1 is divides n, right? For a large range of parameters, not like complete, but and the scheme is very simple, number 1, and there is no complex multiplications and none of these involved. So that way it's like very, very doable, and it is a very simple scheme, right? So the next scheme, which kind of lifts this condition that s plus 1 has to divide n, and achieves the lower bound for all parameters, is based on cyclic codes. Okay. And as you can see, actually here, so one way to think about it is, so there are these worker nodes w1 to w4, and the data partitions which are assigned to them is in a cyclic fashion. So w1 is assigned d1, d2, d3, w2 is assigned d2, d3, d4, and if you look at the actual encoding metrics, at least the non-zeros are somehow arranged in a cyclic way. Okay? So that's what the code means, right? And this can be done for any s and n, right? So but in this case, the simple thing like just taking the sum will not work. We have to take some non-trivial linear combinations, and though so one way is find them explicitly. Even explicit codes are available, but for the purpose of this talk, we will just say that you can pick the coefficients in a certain way, right? It's not that you're going to pick all the coefficients independently from a large enough field. Okay, that, and in this case also, one more thing which I sorry about mentioning the field, actually that thing is coming from coding theory. One major thing to note in this particular problem is that all these are real numbers. Okay, so that is always that's where we are differing from, let's say, conventional coding theory. So there's a question. Oh, the linearity I was mentioning is only with respect to the samples. Maybe, I was not referring to the actual function there being linear. So that is, maybe it's a loose word in terms of linearity that I have used. Okay. Yeah. So how do they pick these coefficients? One thing is, all these coefficients cannot be like picked independently from the real field. That will work, I think, but the only catch here is that, you know, all one's vector has to be in the span of that, and there is no escaping that, right? So that is something we want to make sure it happens. Okay. And for that, a different way of picking coefficients is discussed in the paper. I mean, it's not like just picking them randomly from a high enough field. So that's not what it is, but a slightly more involved way of picking coefficients. Okay. But more or less it is like random, but you have to make sure all one's vector is in the span. Okay. So that is an additional condition that you have to ensure. Okay. And as such, going through how to pick the coefficients, that argument, you know, it's quite long and maybe not too informative here. Okay, so I'll anyway skip that, but they can be always picked. Okay, so that is the point to be noted. So this kind of solves the gradient coding problem itself. Okay, so but then we will go to approximate gradient coding and again motivate that, right? So the full gradient recovery has S+1 data subsets, and to each worker, right? So suppose if the number of stragglers is something like which is linear in the number of workers, okay, with the linear meaning a fraction, right? So in that case, the amount of computation that each node actually is doing is again linear because it is S+1, so that's what it is, right? So one thing to note here is that the gradient coding itself is a part of a bigger problem, right? I mean, our gradient descent itself is part of a bigger problem. You have that, you know, you have to learn some parameter, right? And the actual computation of the gradient itself, right? Even if there are errors in it, the problem, I mean, the way it is done to solve that problem, it is robust, right? So that way, it's, I mean, the requirement that we have placed in the gradient coding problem, that we have to recover the exact sum of these partial gradients, is too much. Okay, too much of a requirement that we are placing for the, you know, for satisfying the original problem. Okay, so in the approximate gradient coding, that thing is relaxed, and relaxed in different ways. And relaxed for good because we are going to reduce the computation for worker. That is the main motivation, right? Making sure that the performance is not affected that much. So we have to kind of keep both things in mind. Okay. And yeah, so though there have been actually approximate gradient coding works before this paper, I'll be discussing results in this paper because there are kind of both converse results and achievability results. So there have been, as I said, approximate gradient coding is the next, you know, a natural thing to ask once we have the gradient coding setting. But the previous works, as I see it, did not have converse bounds. Okay, so and that is why maybe this, yeah, this is titled fundamental limits because there are both achievability and converse results. Okay, so I'll discuss this and then I will discuss our work because I think it's important to place our work in context, and for that, the results in this paper I'll discuss in somewhat detail. Okay, so now we are going to exact recovery, in the sense that means exact gradient computation, that's what it is, but with very high probability. So this is what is the first setting that we want to look at, right? So this G0 is a set of all encoding matrices, and here we are actually, they are like I think I have mentioned n by k or k by n, one of those, right? And here for, you know, for many code constructions and so on, they kind of choose k equal to n. Okay, and that is you can choose more k, but that is not required. Lesser k, I'm not sure. I think there is I mean, it may give some suboptimal results. Okay, so lesser k is always helpful, but then it's not chosen. So the k which is chosen is k equals n for these I mean, many code constructions. So here encoding matrix is of size n cross n over real numbers, and we are looking at the probability, right, that you know, how close we can get to this all ones vector. So that is what we are measuring using AS transpose U. Okay, so this AS transpose U kind of tells you that AS is a submatrix of the A, right, which has only, let's say, n minus s rows in it. Okay, because I'm looking at only non-straggling nodes, right? So what does AS transpose U do? It is like taking linear combinations of the outputs of the non-straggling nodes. Okay, which linear combination, that is okay, because I just want to get as close to the all ones vector as possible. So you're going to minimize over U, AS transpose U minus 1, and this 1 means not just a scalar, it's an all one vector, right? And you're taking the norm of it. And what is this saying is that this probability that it is strictly away from 0 is O of 1. So what is this probability over is a set of all S subsets of this n workers. Okay, so what is meant by with high probability here? Where is the, over which are we taking the probability? Is that we are assuming that we are picking S size subsets of n, all of them equally likely. Okay, and that is the probability. Over that space is where this probability is calculated. Okay, so what in effect this is saying is that if there are some subsets for which I am, slightly away from 0, it's not exactly 0. So all ones vector is not in the span. Okay, but the collection of these subsets forms a very small fraction of the all the subsets. Okay, that is what this O of 1 means. So is this clear? I can just pause because this is important. Okay. So yeah, please type in questions anytime. I'm looking at the chat too. So yeah, so this is what is called a probabilistic relaxation of the previous gradient coding problem that we had, right? And it's a slightly, easier requirement to meet compared to all n minus 1, all n minus s non-straggling nodes having all ones vector in the span. So then in this setting, what is the theorem? The theorem says that, the computation load. So we are actually optimizing over all the encoding matrices because we want to pick the best encoding matrix anyway, right? So this min over the min with a as a parameter is like just saying we are picking the best encoding matrix, right? And this kappa of A is the maximum row weight of A. Okay, and if the encoding matrix is A and the row weight just signifies that it is the number of, maximum row weight means what is the maximum number of data partitions that we are assigning to any worker, and that we can think of it as a computation load. In the previous things, the two schemes that we have seen, and even in the bound that we have seen, right, we were assuming this somewhat uniform, right? So that each worker is giving somehow, doing the same amount of computation. Okay, here that is not the case, means at least that min and kappa definitions just suggest that, it's allowed to vary. Okay, and the computation load is determined by the maximum row weight of A. All right. So what is the takeaway from this theorem is that it is just greater than or equal to this quantity log n divided by log 1 by delta. In particular, suppose if s was linearly increasing with n, then the lower bound that we have is only O of log n. Okay, whereas the previous one which we had was, O of n, right, s plus 1. So that's what we had, right? But here in this case, it's just O of log n. Okay, and that's the improvement that we get by relaxing the gradient coding problem to this approximate gradient coding problem. Okay? And the proof of this theorem itself is, done using inclusion exclusion kind of principle, but then some approximation to it. Okay? So approximation meaning because we don't know exactly, given an encoding matrix, it becomes very hard to find out all the unions, intersections of sets, and that is what is required to actually determine the kappa. But instead of doing it exactly, we can approximate it or get bounds for cardinalities of these sets, and that is the approximation to inclusion exclusion principle, which is used in the paper to derive this bound. sorry, yeah, right. So, and the one which achieves the previous bound also is the fractional repetition code, right? And the idea is similar from before, just that instead of dividing it into, groups, s+1 groups, right? I mean, I don't remember if it is s+1 or n by s+1, whatever it was the notation. Yeah, but instead of that, we divide it into actually larger groups with smaller number of assignments per worker. Okay, so this d is going to be very small, and what is shown is that with this choice of d, which is log n log 1 by delta by log 1 by delta, right? The all that which is different from the previous bound here is just this factor log 1 by delta. With this choice of d, right, it has been shown again that I think even in the proof of this also there is some inclusion exclusion principle only which is used, that the computation load, if we pick such computation load and do a fractional repetition code, then we'll be able to satisfy this condition for recovery, right? Which means that there'll be negligible fraction of sets in which your all ones vector is not in the span of that, right? But that is all that we wanted. So for exact recovery with high probability, we are still okay with fractional repetition codes with the repeating factor or this whatever d parameter picked carefully. Okay. And it is asymptotically optimal because this factor doesn't matter when n is going to infinity. So the next one is approximate recovery, again with high probability. So here the difference from the previous thing is that we are even allowing for error here. Okay, so we are not saying that minimum when is it strictly greater than 0. So that's not what we are looking at. Okay, we are only asking for the recovery error. We are only asking for the recovery error to be greater than some epsilon n. So that sets have to be small. So here this epsilon factor is some, I mean, it's called recovery error, I think. I forget the actual term, but I mean, as you can see that this epsilon kind of relaxes your thing further. But how much improvement does it give is what the next theorem tells you. I mean, if you relax this much, so which means one, we are doing probabilistic relaxation already, and then again we are asking that the minimum can be slightly away from 0, which is determined by this parameter epsilon. Okay, so if we impose both the conditions, then this again the theorem says the computation load is lower bounded by some quantity, which is something like log of 1 by epsilon divided by log of 1 by delta. I mean, if you asymptotically, it's that factor. I mean, if you neglect this n inverse here, right? So earlier what you had when you had exact recovery was you had log n divided by log 1 over delta, right? Here in this case, what we have is it is log of 1 over epsilon divided by log 1 by delta. Okay. And in particular, suppose if, yeah, so you pick stragglers in some way, which is again linear, the previous case, and you're picking epsilon as 1 over, so let's say log n, then the lower bound is log n, which is again much smaller than the previous case. So we are getting two advantages. One is, I mean, in the previous case, when we said that it has to be exact recovery with high probability, right? The computation load was of the order of log n by log 1 over delta. And here in this case, when we also relaxed that it can be away from 0, bounded away from 0. So in that case, we get a lower bound as log n. Only thing is, of course, the fractional repetition code does not achieve it. So the authors of the paper, they do what is known as batch raptor code and show that it is asymptotically optimal. So what's a batch raptor code? I'll just give a very, very brief description of the code. So what you do is that you have these gradients, I think, let's say G1 to Gn. You divide them into batches of size, and they're all disjoint. So n by b batches of size equal to b, right? And do a Raptor code on each batch. So what happens in the intermediate nodes here is that already one sum is taken. Okay, so which means that G1 plus up to GB is already taken. Okay. So what happens with the workers is that, so for going from N over B batches to the workers, right? So there'll be batches assigned to the workers somewhat randomly, okay? And that random choice is based on a certain degree distribution, which is, in the literature of Raptor codes. And that is the reason this is called batch Raptor codes. Okay? So because what is actually going as input to the Raptor code is these n by b batches of gradients, right? So I mean, if you don't know the Raptor code, I think at least as part of this talk, I'm not going to go through a whole lot of detail to explain that. It is fairly standard, and in the again, the Raptor code itself is very easy to implement, right? It's just coefficients are coming from either zeros or ones. There are no real coefficients here in this whole thing going on, right? And the second interesting thing in this whole thing is that you can do what is known as a peeling decoder, right? To get all the batches and then take their sum. Okay. Maybe there is another way to do it also. Just take some linear combinations which works, but this definitely works. Okay. With high probability, it will definitely work because we are recovering individual batches by decoding the Raptor code itself when the master gets it actually, right? And once you do the decoding, then you can take the sum of all the batches and then you get the full gradient. And so here, if you see, the peeling decoding algorithm itself is successful only with a certain probability, and that we are fine with it, okay, because we have that in the recovery error too, right? So that factor we are having it to play with. So that is why the Raptor code is helpful in this case. If it were exact, maybe it's not. Yeah. Yeah. Okay, and the average computation load is asymptotically optimal. As I said, the computation load is log 1 over epsilon divided by log 1 over delta. Maybe some factors are missing, but this is asymptotically optimal. Okay. So now the next question in the approximate gradient coding that we ask is, can we do partial gradient recovery? Okay. So there has been a paper which does partial gradient recovery. In this paper by Hanna et al. Okay, so but what they are asking is the following. Okay, so I am not asking for full gradient. I'm only asking for the sum of k fastest gradients, and I'll forget the rest if I receive the first k. Right. So in this case, it's always good to keep this trade-off in mind because as we said, the actual place where these gradients etc are being used, it's somewhat robust. Okay, but again, it is happening in iterations. Okay, so that is so that nature of iterations, whatever is going on, is the trade-off which is mentioned here. What it says is that suppose if k is small, right? So which means that I'm only waiting for some k, sorry for the overload of notation. Yeah. So but if k is small, which is the k faster to the gradient, suppose if I use them, right? If k is smaller, the computation time is better because I'm asking for much smaller number of gradients in each round. Okay. But generally the convergence is worse. Okay, because what determines the convergence in the actual algorithm wherever this gradient descent is being used is, I mean, if you can qualitatively say, it's the quality of the gradients, and the quality of the gradients is determined by how much data you are using to generate the gradient itself, right? And if you are using only a part of the data to generate the gradients, which is this partial gradient, then the quality of the gradient itself is not so good, in which case when the quality of the gradient is not good, then the convergence is slower. Okay, all these are qualitative statements, but at this point I just want to make qualitative statements for understanding. Okay, so I think maybe yeah, it may be hard to even quantify them, but there have been some analysis which do that as well. Okay, So if k is bigger, I mean if k is larger, then of course the convergence will be better, but the computation is worse. So, and just remember that whatever gradient coding etc we are doing is for one round. So whatever I have described till now, this happens every round of gradient descent. Okay, so this is what is a trade-off which comes as part of partial gradient recovery, and the setting that we look at is coding for partial recovery. So previously when they did I think gradient coding for partial recovery, but maybe they would have used maybe they would not have they would not even have had repetition codes, let's say. That's my understanding, but we use coding for recovering partial gradients. So we have n workers, k data partitions, right? And in this case, actually, what we do is that we also allow for multiple linear combinations that each worker can send. Okay, so this is somewhat important, and I think some of our schemes say that we can also do with single linear combination, but the most general scheme that we have requires multiple linear combinations of the partial gradient at a node, at a worker, to be sent back to the master. um, and yeah, so this, for the problem of partial recovery, this is required. It's not that, I mean, we cannot always do away with a single linear combination. But what is the aim at the master itself is to recover the sum of gradient of any alpha k data partitions where alpha is a fraction. Okay, alpha is given to us, it's a part of the problem, but then we are only asking that the sum of gradients of any alpha k partitions have to be recovered at the master. Okay, and L is again a parameter which is a fraction, and I think, yeah, so L into k is the number of data partitions that we are assigning to each worker. Yeah, so here with this, all these parameters, we call our schemes as alpha is feasible. So there are enough number of parameters, so all those parameters gradient coding scheme. Okay, and all those parameters are part of the problem, right? And with this, actually computation load is again actually known to us. It should be related to the L parameter, right? But the communication cost also will come into picture, because here we are saying this M is somewhat indicative of the communication cost. Okay, because earlier it was always 1, but here in our formulation of the problem, we have to worry about that also. Okay, so we have a lower bound on the computation load, which is something like this. It is s choose y, I mean, given all these parameters, s choose y divided by n choose y, it should be less than or equal to 1 minus alpha. So this kind of gives a bound. I mean, you have to turn it slightly around to say what is how it gives something on the computation load, right? But this I mean, it can be expressed in terms of these parameters again, the computation load. Okay, so as such, this bound, how it is giving a lower bound on the computation load is not clear, but it can be turned around. Okay, so some things to note. This bound, how does it compare to the other approximate gradient coding problem number 1, right? So if we plug in the parameters carefully by choosing s as linear in n and so on, right, we get the same factor as them. Okay, it's like it's again going to be the exact recovery with high probability. What is the computation load that we had? It is log n divided by log 1 over delta. It is similar parameter that we get in the asymptotics here. Okay, so that way we are not getting a very different bound from what was there before, but just that it is a more combinatorial bound, as you can see, right? And the reason the bound itself is combinatorial is because our condition that we have placed, the requirement that we have placed is combinatorial. Okay, we are saying the master should be able to recover any alpha k data partitions, which is a more combinatorial requirement as compared to the approximate gradient coding condition, right? And the bound naturally tends to be combinatorial. Okay, And it can be seen again if first for a proof sketch, right? The first step that we kind of do, and it kind of gives us the bound, but then you have to add more ingredients to it to actually prove the bound in full generality. But to quickly see why this kind of thing works, right? So again, we have, assume that I have this, j equals 1 to n choose s, all possible subsets, right? And the number of data partitions are also that much, which is n choose s, which is very, very large, as you can see, right? So this is assigned. So every data partition is okay, wait a minute. um, yeah, sorry, the number of data partitions will be just I think maybe n choose y, so that's what it has to be. Okay, so here I have not exactly mentioned what it is. So but each data partition is assigned to a unique subset of y workers, right? So that way I think it has to be n choose y. Okay, so with that number of data partitions, again this particular small argument that I have given you is counting in two different ways. Okay, in one way, when we are counting, what we are saying is, when I have n chooses stragglers, right, and looking at the total computation load for all possible subsets, because for each one it has to be k into 1 minus alpha. For all the n chooses values, it has to be k into alpha times n chooses. Okay, and so that actually gives you an upper bound, and what is on the left is the exact counting. Okay, so with two ways of counting the same data partitions assigned to these workers, exactly the same thing that we did in the gradient coding problem, but here it is slightly more complicated because the assignment is like based on this unique subset of y workers. So that is the only difference, right? So with that, just using counting in two different ways, we get the inequality. Okay, but again, this thing that each data partition can be assigned to unique subset of y workers, it's not the most general way of gradient coding, right? But when we are proving a lower bound, of course we assume a more general encoding metric, so we relax it and still do a longer argument to show a similar kind of a result, right? So that is all things about the lower bound. And again, as I said, it is asymptotically same as the approximate gradient coding bound, right? So how do we achieve this? So achieving is much more simpler, just looking at the expression itself. Okay, so it's what I call, we kind of colloquially call, though maybe we did not write this in the paper, but we call it Ali-Neeson kind of scheme, because in coded caching literature, it is a similar trick which is done, right? And the coded caching paper by Madali and Neeson, right? So we call it a combinatorial gradient coding scheme, and the full data set, yeah, as I said, has to be divided into n choose y data subsets, and each data subset is indexed by that subset. Okay, and when do we place a particular data subset in a node? If it is contained in that index. Okay, if a particular worker index is contained in that subset index, then we place it in the assign it to the worker node, and not otherwise. Okay, and with simple counting, we can also know that, we can show that the number of data subsets assigned to each worker will be n minus 1 choose y minus 1. And the reason I was telling about this computation load is that at least we have not been able to get a good non-trivial scheme till now, where we take linear combinations and send it back to the master. Okay, take small number of linear combinations and send it back to the master. So the only way at least this combinatorial scheme, which achieves the lower bound with equality, works is that it sends individual gradients by themselves, and we can slightly optimize it, but not too much. Okay? And that is the reason I was saying that for this combinatorial kind of partial recovery problem, right, it is important that the number of linear combinations that we send be high. Okay, otherwise we will not be able to guarantee the requirement. Okay, and the previous thing also can be achieved with T designs, because actually T designs are objects which are very symmetric, It has a whole lot of parameters, but all that it says actually is a description of an incidence structure. Okay, so there are something like points and sets, right? So there are mu points and some number of subsets, right? And with the property that every T subset of these point set, right, is contained in exactly lambda blocks of B. So this is a definition of a T design. And if you see the way we were doing before, right, so this n choose y and so on, and if you look at the incidence structure of that, it is a very trivial T design in some way. Okay, so and but one good thing is this particular trivial design exists for all parameters, right? But if we want a more non-trivial T design, that exists only for certain parameters in the design literature itself. Okay, but the thing is, suppose if T designs exist for some parameters, then we can use that incidence structure instead of what we were doing before, right? And get actually much lower, let's say, this if I want to call it a subpacketization or whatever partitions we are doing, right? The number of partitions we are doing, we can reduce them by going to T designs. But the only catch is T designs do not exist for all parameters. So for parameters for which T designs exist, we can always do this trick. Okay, and again, that incidence structure is kind of giving you which data partition has to go to which worker. So there are a set of points and there are a set of subsets, and this B, whatever was there as part of T design, okay, they correspond to, I mean, each one of them corresponds to a data partition, and the S, which is part of T design, which are points, are just workers. Okay, and the incidence structure of the T design will exactly tell you where into which worker which data partition has to be kept, right? Yeah, so then we look at maybe in the interest of time, I will just skip a few slides, not to go through I mean, I'll summarize what's going on here, but not go through that in too much of detail. Okay, so the question to ask is the partial recovery not possible at all with small communication costs? It's not like that. It is possible, but for again, subset of parameters, right? So I don't know where I have given the summary. Oh, yeah. So this is a summary. So here we are looking at cyclic gradient coding schemes. So inspired by again cyclic codes which were there for full gradient recovery, can they be used for partial recovery as well? Okay. So we still want to use a communication cost of 1, right? So and the kind of computation load that we are looking at is not S plus 1, but with some, what I would say, a back off from S plus 1. So we have to reduce from S plus 1 because S plus 1 already was giving us full recovery, right? And what is the amount by which we are reducing is n minus beta, okay, where beta itself is alpha n. Okay? So it's like n minus alpha n, that much we are reducing from S plus 1, okay? And we are looking at whether it is possible for cyclic schemes to exist. So we have some results which are like, again, we are looking at cyclic schemes with communication cost 1 and 2 only. I mean, the lowest possible ones. And also, so the first thing is, if a certain divisibility condition is satisfied, yes, cyclic codes exist and we can do partial recovery with that. Okay. The second one says, the second line, the way to read it is that suppose if one divisibility condition is not satisfied, then there exists no cyclic coding scheme, okay, with that computation load. That is not possible. Okay. So which means that we have to, then we show again that, again, not for all parameters. So there is certain divisibility condition which is required for communication cost 1. If the divisibility is not satisfied, we are in the regime of this lower bound. Okay. So, but then it becomes a case for communication cost of 2. Whether it is not that, again, with communication cost 2, I can cover all parameters. Again, there is, a slightly larger class of parameters for which we can show the cyclic codes actually with communication cost 2, right, can be used for partial recovery, right? So that is the way to understand this. But then again, so it was like, we were looking at very specific schemes a cyclic gradient coding scheme, and we were restricting the communication cost to 1, and with that we can show some form of achievability and converse. Okay? And the reason it's like, even extending any further, it only non-trivially generalizes the problem. So it's not like straightforward extension to more communication costs or whatever. Okay, whether we can cover all parameters, it's not, because the way to prove either whether 2 works for all parameters and all that, it becomes highly non-trivial as we increase in the space, right? So that's the reason, I mean, again, so because we have to keep track of so many subsets, and how how the subsets are interacting with each other, number one. And the second is, here it was easy for us to do for 1 and 2, because in this case somehow it was easy for us to show that it was actually enough to take the sum. Okay, so but it becomes highly non-trivial when we allow for linear combinations. So in the schemes that I have described, even with the combinatorial and cyclic, as you have seen, all the encoding matrices, they were just zeros or ones. Okay, and the way I think about that problem is that you know when you want to assign lower computation load to each worker, right, it's as if in the encoding matrix you have a whole lot of zeros, right? And with this whole lot of zeros, it's not possible to take non-trivial linear combinations and make one somewhere. Okay, so it's like either mostly all the sum of vectors will be there, or otherwise you are sending them as it is. So these are the kind of schemes which we kind of saw, but I mean, I think I can say that we were not able to come up with a scheme where we take some non-trivial combinations which had coefficients, let's say not 0 and 1, right, and show that either it works or doesn't work, right, for when the computation cost goes lower and lower, right. It actually poses a problem. It's not so, because you cannot take a whole bunch of zeros. If there is a whole bunch of zeros, it doesn't make sense to take non-trivial linear combinations. Okay, so that is, I mean, that is one, just a high level remark that I want to make regarding these schemes. Okay, yeah, so we also have some general lower bounds, but these are again for low communication cost, but then again with very low computation load as well. Okay, so we have a lower bound which says that, and this is not for cyclic schemes, it is in general. So what we say is that there exists no GC scheme with a communication cost of 1 and a computation load of, let's say, 2 by n, okay, for a certain value of beta, okay, for class of beta, actually for odd beta, right. This is again an impossibility result, which means that it doesn't make sense to try out for communication cost of 1 and 2 by n. It doesn't make sense when beta is odd, right. But then again we have some lower bounds and achievabilities there. But one thing to note, as we have been seeing, is that in the full gradient case, both the minimum points are possible simultaneously, which means that you can achieve minimum computation load with a minimum communication cost. Okay, whereas for the kind of partial gradient recovery, that is not possible. There is a trade-off, but the trade-off is not so neat. I mean, it becomes more piecewise, and sometimes it depends so much on the parameters and all that. But there does exist a trade-off between computation and communication cost, and if you want to go closer and closer to the computation load of the lower bound that I have shown few slides before, right, it is required that we go to higher communication cost. But whatever we may be doing is too much of an overkill, and choose y may be too much, but certainly it is more. Okay, so this I
Lalitha,
think, yeah,
so we are at 10. Should we sort of,
yes.
it seems like they are on a tight schedule.
Yes,
Uh,
yes, yes. So
yeah.
I will skip the next part of the talk itself, but I'll just show the simulation and I'm done. Okay. So, I mean, in since a few slides, the next topic I'll skip because the tired gradient
Awesome.
codes. Yeah, yeah. So, So just a quick comparison that we have done, because these actually, I mean, all the schemes generally are compared against real data sets on which gradient coding is performed. So we looked at the task of classifying handwritten digits from an MNIST data set, and the goal was to train a two-layered neural network with some number of nodes and some labeled images. The gradient descent itself was performed using cross entropy laws. Okay, and again, so there are a lot of choices that we have to make on the way as to what is the computation time of a gradient. It is distributed as Pareto, but then with a certain scaling model. Okay, because uh, so there are multiple there are varieties of scaling models which kind of model the computation time in literature, and we chose one particular thing in there, which is called data dependent scaling. And at least for the data set that we have chosen and the parameters, the cyclic scheme was performing better than even batch raptor codes, but then the FRCs are like just too fast. Okay, but the only way that we make a case with FRC is that FRC fails if the stragglers are like concentrated among a few sets. Okay, because as you can see, if you somehow straggle all the nodes of a particular group, then FRC kind of fails, right? So it's like more structured straggler patterns, which where we are kind of outperform with respect to FRC. But if it is always picked random, yes, FRC performs very well. Okay, I'm even slightly better than our scheme too. So that we understand. And the case that we make for the cyclic schemes is when uh, you know with respect to FRC, it's when you can have adversarial straggler patterns too. Okay, whereas for with respect to all the other schemes, we kind of outperform, and that is with respect to testing set accuracy against the wall clock time itself. So that is the plot which you see there. Okay. So at this point I will stop, because the next thing will be in a different topic and I don't have time. Thanks, Vinod, and thanks for this small extra time that I got. I think 2-3 minutes. Yeah.
Thanks, Lalitha. So, Satyajit, do we have time for any questions or should we just move on?
Yeah, we have time for a couple of questions. So next
Okay.
talk will start in 5 minutes. Yeah.
Okay. So, please put your questions in. Maybe I can ask while people are thinking of questions. So, Lalitha, is there any benefit in gradient descent to late? Like here, I guess the premise is that if a straggler, if there's a straggler and you get the results late, you just can't. I mean, you're not planning to use it, right? So you want to make sure that with whatever we get, you can proceed with the gradient descent. But as you mentioned, this is because this is just one step in the descent. So you're doing this over and over again. Is there any point in a late? So you just received, say, one of the workers returned late. Can you use it in your next step and so on, or?
Um, so yeah, I know that some such work is there. I think there is work by maybe Gauri Joshi and others I mean, the title of that is "Slow and Stale Gradients Also Win the Race," kind of,
I see, I see.
right? So, but I mean, yes, there
Would
is a
that
case to
sort of
that.
suggest a different way of, I mean,
Yes.
another dimension for
Yes,
how you're
yes,
looking at it as a
yes.
coding scheme?
So
So
it's
maybe you
called,
can.
I mean, so it's called either you're doing synchronously or asynchronously, right? So that's what is the thing. So asynchronous also are there, but there, I think, I mean, as far as I understand coding, I don't know if it's studied in the asynchronous context. So I
I see.
think studied more in the synchronous context, but yes, there are, I mean, so that is being studied as, how it performs against just plain gradient descent, right? So that's what, yeah. And still there are works, in the sense there is ongoing work. Yeah.
I see. So yeah, please put in questions. How about? So you mentioned. I mean, This is a very practical problem. So how do people look at it? Practitioners look at coding. Is the sort of extra overhead justified for them, or they?
Um, See, the way I would think about this problem is, for me, I would be happy with fractional repetition. Okay, if I was a practitioner, I would be happy with fractional repetition, and that is something I think maybe they are fine, because repetition in some way is there. Okay, but if it is already giving advantages, yes, why not, right? So, and if it is like very simple schemes, maybe just things which you add and send, right? Even that, maybe they might be willing, but not currently, with some amount of, it has to fit the use case correctly, right? So if it fits, so right now maybe they will not look at it, so that maybe they look at fractional repetition. But just taking simple linear combinations where you just need to add a few things and all that, that I think still they might look at. So this is only a guess that I'm making, because see, finally it's who are running these jobs, right? I mean, machine learning jobs are being run by everyone, right? So who is I mean, it's actually different from even caching or the storage problems, because there it's like there are central people who are actually maintaining the system, and that's where things go into. This is like anybody who wants to actually speed up their jobs can do it for their tasks, right? So it can be at more decentralized level, means in the sense individuals can start using it, and we might not even take a notice of it, perhaps.
I see, I see.
Right.
Great. So there is a question. Is there any benefit of allocating data partitions cyclically, and how k is dependent on n in that case?
uh no, I mean, so cyclically is just one way of doing it. So basically, any support structure which satisfies the MDS condition. So there's a certain MDS condition which needs to be satisfied, and any support structure which satisfies the MDS condition is equally fine. So there is no benefit as such of assigning them cyclically. It doesn't reduce any complexity or anything. Okay, and k is equal to n for the case of cyclic.
Okay, thank you. So I guess we are finishing on time.
Okay, okay.
Satyajit, I'll hand it back to you. Thank you, Lalitha, for this very, very nice talk. Thank you.
Thank you, Vinod.
Yeah, thanks Lalita, and thank you Vinod to you too. In this very busy schedule for you, you came and chaired this session. Thanks a lot, both of you.
Thanks,
So
Vinod. Thanks,
yeah,
Satyajit.
if you
Yeah.
have time,
Yeah,
to join for the next session. Thanks.
bye bye.
Bye, bye, bye. Yeah.